Hands on, everyone. Let's start off. Last class we have finished with magnetic force and magnetic field. Today we'll be starting with electromagnetic induction. Important chapter. Just like in mechanics we had rotation, in electromagnetism we have EMI. It's a pretty good weightage topic. So the first thing, magnetic flux. So what is magnetic flux? It is the same thing like that we did in Gauss law, electric flux. So technically there is no difference between them, except one is based on electric field and one is based on magnetic field. So flux is proportional to the number of lines passing through an area. So if 5 lines are passing here, 5 lines are passing here. So end of the day, in each of them, 5 lines are passing in all of them. So they have same flux. You should refer this to Gauss law, the first 2 pages. Exact same stuff if you see. Nothing, there's no difference. And if you remember, there's a statement here. If you study flux in terms of field lines, it does not depend on angle and area. But if you study in terms of electric field, then it depends on area and angle. Because field and field lines are not same. Field is number of lines per unit area. So the argument is still the same here. We can say the same thing here. They have the same flux. So refer Gauss law page 1 and 2. So here the magnetic flux is given by integral B dot dA. If B bar is constant, it comes out of the integral. Then your flux becomes B bar dot A bar, which is BA cos theta. So if this is your area vector and if this is your B bar, theta is the angle between them. Clear with this? There, that is our first formula for the flux. In Gauss law, this was E dot dA. Here it was B dot dA. So if the flux is same, so do we have anything like Gauss law also here? So if you try to apply something like Gauss law, see, mathematically they look the same. Max doesn't care whether you want to call it as electric field or magnetic field. So if you try to apply Gauss law for magnetic flux, luckily the answer is integral B dot dA. I hope you remember the meaning of that symbol. The moment I put that circle means you're integrating over a closed surface. This is always 0. If I don't put that circle, meaning the surface is not closed. If I put that circle, meaning it's a closed surface. If it is B dot dl, that is a closed loop. It's called a closed integral. So why is the flux 0? You can explain this in 2 different reasons. One, magnetic field lines always form closed loops. Even the lines which you have taken till infinity, they would turn around at infinity and form a loop. So magnetic field lines always form closed loops. Means if you have a closed surface, the magnetic lines will be like this. So the number of lines entering and leaving will be always equal for a closed surface. If the surface is not closed, then it need not be zero. Isn't that the definition of flux? Number of lines crossing. If 10 lines enter and 10 lines leave, there is no flux. This is one way to explain. Second thing, if you remember in Gauss law, flux is nothing but charge enclosed by epsilon. In magnetism, we don't have anything called charge, but we have something similar. So there we have positive charge and negative charge. Here we have North Pole and South Pole, isn't it? So North Pole and South Pole is for magnetic field, plus Q and minus Q is for electrostatic field. So the magnetic monopoles don't exist. Unlike electrostatics, where you have a plus Q charge and minus Q charge, you will never find a single North Pole and a single South Pole. Poles, they always exist in pairs. That is north and south, you'll always get as a pair. That means plus Q minus Q will be always together like a dipole. The total charge will be always zero. I think, but last 4 5 years back, they did actually find these monopoles in a very low temperature surface and all. Hypothetical thing, we'll not get into that. So normal things, it works. In some extreme conditions, they did actually find. So therefore, we call this thing pole strength. We will study this in bar magnets. So you can simply, for now, think of pole strength as magnetic charge. So stronger the North Pole, the more charge it has. So it resembles. So you can call North Pole, South Pole as magnetic charges. North Pole is plus Q and South Pole is minus Q. Since they always come in pairs, then if you try to use Gauss law, flux is nothing but charge enclosed by epsilon, and charge enclosed is always zero. Is this clear, everyone? That's it. So that is the thing. The only formula I taught you is flux, which is integral B dot dA, which you already learned in Gauss law. Any doubt so far? So we don't have Gauss law in magnetic flux, so you're saved. But we did have Ampere's law in the last class. So that takes care of that thing. Let's see some questions on flux. So we have a magnetic field region. This is root 3a. We have a equilateral triangle, side A. This distance is also A. Magnetic field is B, and this thing is going with constant speed. So that means this triangle, right, will enter inside like this, will go inside, then will start coming out and then comes out. So the triangle is continuously moving through this region. Plot flux versus time graph. Plot flux versus time graph. The only thing I taught you, flux is B into area. Rest is all geometry. Any ideas? So when this is entering inside, you are interested in this area. Let this be x, let this be theta, let this be theta. This guy will be 2x tan theta. Theta is 30 degrees here. So that area will be x square tan theta. And we can clearly see that x will be equal to ut. So flux will be b into area, which is bx square tan theta. So flux is proportional to x square and x is proportional to t square. That much, I just want the graph. So similarly, when you are leaving, again, this t is not the t from 0, okay? This is the t when you're about to enter. Similarly, when you're leaving, I'm taking this as x again. Same story, this is theta, but this time I want the area inside, isn't it? This area I want. This area will be some constant minus that bx square tan theta. This will be the total area. So now if you try to plot this graph, so for initial some time, there'll be no flux. That is still a by u. Then it's a 1 by t square function. It's a parabola. Then it becomes a constant. If you see, the side is root 3a and the height of the triangle is root 3a by 2. And if you notice, while coming out, if you see the function, it is minus x square. It is a downward parabola. Looks like this, isn't it? That's how the graph looks. It's a minus x square function. It's a downward parabola. So the flux will be like this while leaving. This is while entering. And this is when it is inside. So for some time, the flux will be constant. Clear, everyone? The most common mistake that I see people doing, they draw it like this. That is the most common mistake. You draw it like this. It's a downward parabola. You can actually check it out. If you differentiate this dA by dt, you will get a negative slope, isn't it? Which is increasing. So the slope should increase in the negative. It should be more steeper as you go. Clear the graph? There, more of a geometry than actual question. Let's see one more. Any doubts on this? Flux question. So I could have asked the same thing in electric flux also. Infinite wire, square loop, side A. Again, remember what is flux? B dot A. So B is created by the infinite wire. So that is passing through the square loop. So find the flux in the square loop. This is a ring. Find the flux in the ring. Two different questions. The first one is the standard mains level question. Second one will be a good one. Second one, they'll actually ask you in mutual inductance. Later on, I'll show you. So these are infinite wires. There is a square loop at a distance d. In the second case, there is a ring which is touching the wire. Find the flux in both of them. Two different questions. So second one is a good one. Both are important. The first one is a pretty standard mains level question, came multiple times. Second is something else. Get this first one, you should have got it first. Second one, I'll help you for some time. 1 minute for the first one. Right, Rehan. Get the second one. Let's see the first one. First was easy. Most of you got it. Yeah. Second is important one. Try second one. I'll give another 2 minutes. So how do we handle this? At a distance x, take a thin strip. Because at every point here, if you look at the magnetic field is into the plane, B naught is mu naught I by 2 pi x. Field due to an infinite wire. The field is changing at every point, so you can't directly do B into area. So it will be B into the area of that strip will be, the side is A dx. Angle is anyway 0 degrees, so B and A are parallel. So this will be mu naught I by 2 pi x A dx. Limits will go from D to A plus D. Therefore, the flux will be mu naught I A by 2 pi ln A plus D by D. Clear? That was easy. So you take a small element and then you integrate flux for each part. Flux is a scalar quantity. Anything, dot product is a scalar quantity. How do you find for this circle? Circle, the headache is how do you choose an element? Now, one thing I'll tell you, see, whenever you see a circle, you should always take an element from the center only. You cannot choose anywhere else. So let me show you how to choose an element. So let's say from center at a distance x, we take a thin strip like this. The problem here is doing in terms of x and y is painful for circles. I prefer always theta. You can do in x and y also because you know x square plus y square is r square. So this is y. Then this distance will be r minus x. Perfect. So what is the magnetic field? The magnetic field on that strip will be mu naught I by 2 pi r minus x. That's your magnetic field. So what is the flux in that thin strip? Magnetic field mu naught I by 2 pi r minus x. Area of that strip will be 2 times y dx. X is r cos theta. Y is r sin theta. So can you do something now? Can you substitute everything there, get dx and then integrate? Theta limits will go from where to where? If you take this point here, theta will be 0 and this point will be theta will be pi. The limits will go from 0 to pi. Can you integrate? I know x, I know y. So substitute here, get dx, everything. Physics got over at that point. Once I wrote till here, physics is done. Now it's your job, integration. Try, I'll give you a minute. This much you guys can handle now. There is, I should get a very beautiful answer. You must have done more deadly integration. This will be a joke. Right, Niharika. You ignore the minus sign. It's anyway magnitude. So substitute here. Integral 0 to pi mu naught I 2 will cancel. Y is r sine theta. Dx will be minus r sine theta d theta. Denominator में that is pi, that is r 1 minus cos theta. Numerator you can write that sine square theta is 1 minus cos square theta. 1 minus cos theta, 1 minus cos theta will cancel. It will be 1 plus cos theta will be left out. You will end up with mu naught I by pi r 1 plus cos theta d theta with a minus sign 0 to pi. So you will get calculate this, you'll end up with mu naught I pi r. Just put a mod. You get a pretty nice answer, mu naught I r. Remember this. Later on, I'll teach you this in right Purvaja. Mutual inductance. There we will need this. So they'll ask you like that, find the mutual inductance between an infinite wire and a ring. And the answer will be is equal to mi. I will cancel, you get m ka value. So something like that we will see later on. So like that, you can frame questions on this. Clear with this? So anytime you see a circle, always try to get something in terms of theta. That is the safest way. X and Y, yeah, you can handle, but yeah, sometimes it doesn't work. ये भी कर सकते हो. Y will be root over r square minus x square. You'll get root r plus x and all. So clear with this? Next one. So this is more of a math problem once you got the elements. So we got a semi-infinite solenoid. So left hand side you can see it, right hand side it goes to infinity. Now when you see the field lines here, this is the field line passing through the axis. Now if you see the other field lines, so multiple lines are entering from this open end. So these green ones are the last lines to enter from outside. So after this green one, there are no more lines which will enter inside. And at infinity, lines will become parallel. So if you see these lines also, right? More lines are generated in the middle of the solenoid because there's not infinity, right? Some lines will be generated from the middle. So eventually at infinity, there'll be more lines. So these green lines are the last ones to enter. So these are the last field lines to enter from the open end. So if you see these green lines, let the distance will be x from the axis and r is the radius. Find x. This is a kind of a question which is easy to solve, but you need to think. Difficult to figure out, but easy to solve. Hope this question is clear. We got a semi-infinite solenoid. Lines are entering from left-hand side. They will not be parallel because there's an open and lines will be all weird. So there are multiple lines. The green lines are the last ones to enter. When they go to infinity, in an infinite solenoid, field becomes parallel. So at infinity, it is an infinite solenoid. On the other right side becomes parallel. So there will be lines, some lines generated in the middle also because there is no symmetry now. So the question is, these green lines will be at a distance x from the axis. Find x. Anyone not clear with the picture, anything that you didn't understand, ask me. You got a minute, then I'll help you out. Everyone got the question? Think for 30, 40 seconds, then I'll show you something, then I'll give another 30, 40 seconds. Why does it matter, Aditya? Without current, where will you get the magnetic field lines from? If you know how to do that, let us know. You'll get a Nobel Prize. We will put you in a generator and get free power. You'll be the savior of humanity. The hint is here. Told you, this will come in the next class. Now see if you can think of something. I'll give another 30, 40 seconds. If the number of lines passing through an area are same, then the flux is same. सोचो. मेरे Purocha. I think you messed up some calculations. You're close by. See, I will just draw a cylinder. So these lines which are entering will become parallel somewhere here. So we know every other line must be between this green line. And we also know, I don't know the magnetic field at every point, but I know the magnetic field of the horizontal components. I know this Bx, 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 Bx. So we know this thing Bx is equal to mu naught Ni by 2. What is flux? B dot area. So you should just take the perpendicular. R square. Dimensions match नहीं हो रहे हैं Niharika. So flux entering will be the horizontal component Bx into area. Because Ba cos theta, B cos theta is the Bx. Eventually, when you take flux here, since you're at infinity, the field becomes mu naught Ni. So here the flux leaving will be mu naught Ni pi x square. Isn't it? At infinity, the field is mu naught Ni. Since the number of lines is same, the flux must be same. Right, Poroja, right, Niharika. Since the number of lines are same, flux is same. So mu naught Ni by 2 pi r square, mu naught Ni pi x square. X is equal to r by root 2. Clear with this? Meaning, once you know what to do, how long does it take? Less than 30 seconds. The headache is figuring out, boss, there is a Bx will be same. So definitely refer this, page 169. Clear with this? That's what makes this problem good. There, we are using that with the flux ka thing. Clear with this? So there, flux ka, you can keep playing like this. You will find something similar to the Gauss law thing. The next thing is the Faraday's law. So Faraday, right, actually used to be a book binder. This we are talking in late 1800s. Books were quite expensive. So people who had books, right? If you have 20, 30 books in your house, you must be damn rich. Right? So it was like that. So Faraday used to be a book binder. So it was a profession. So you get your book and we'll bind it to you and we'll give it. You must have done when you're in school. So this guy used to read all those books. So he's like an, he didn't have any formal education. And that's what makes him, really special actually. So this guy is self-taught. So he used to read all those books and everything. And during that time, right, in London, Royal Society of London for Science, every Saturday, Sunday, they used to have, these big exhibitions. Like, the scientists used to bring all their experiments and everything, and they used to demonstrate and show it to the people there. Like, currently people do it for this stand-up comedy, no? So during that time, there was no internet, nothing. So people needed some entertainment. So science was an entertainment. So people used to get all these things like a magic show and different experiments and stuff. So during that time, the head of the Royal Society of London was Humphrey Davy. Right. So this guy used to, he was very popular and everything. The things used to get full, auditoriums used to be full. So this guy, Faraday used to attend those sessions. He used to sit there and used to make notes out of it. You getting it? And he did that for few years, 1 or 2 years. So, and Humphrey Davy, right? Meaning he used to breathe in, nitrous oxide before starting the session, and then he used to come with a big smile and everything. Nitrous oxide is laughing gas, isn't it? It relaxes your muscles and everything. So kind of tension goes off. But I heard that he finally died because of nitrous oxide poisoning only. So that's a different story though. So he must have gone laughing only. So then, so this guy used to attend all the sessions. He used to make a neat copy out of it. And after 2, 3 years, he goes to Humphrey Davy and submits all his books, whatever he wrote, handwritten ones. Humphrey Davy sees the books and gets really impressed. Like, yeah, this guy must be a big PhD guy or something. Such a neat way of putting the points and analysis and summary and everything. So he calls him inside, and when he sees Humphrey Davy, when he sees Faraday, he's like, yeah, this guy's looking like a beggar. So problem is that no matter how educated you are, if you don't present yourself, people don't treat you well, unfortunately. He sees him and he says, okay, thank you for the books, you can go. So before leaving, right, Faraday tells him, sir, if there's any work, please let me know. I'm ready to work even for free. He was so keen on subject. I actually saw all this thing in a documentary called E is equal to MC square. There is a beautiful documentary there. I saw this when I was in IIT. 1 hour 50 minutes का documentary है. People won't have patience. So 30 seconds में अगर reel बनाएंगे तो देखेंगे नहीं. तो difficult है. नहीं तो Salman can make a movie on Faraday's law. Salman Khan will be Faraday. बीच में 2 item songs होगा, 4-3 लोग से fight होगा. So then maybe people might watch. So anyway, if there are any Salman Khan fans here, so I'm sorry, no offense. Anyone is there a Salman Khan ka fan here? Could be. So story goes like that, and this Humphrey Davy, one day he was doing an experiment with some sodium hydroxide, and that acid, sodium hydroxide falls in his eye. He gets blinded in one eye, and he was looking for some assistant to work, and then he remembers Faraday. He calls him up, and Faraday starts working as a lab assistant. His job was to clean the things and everything and keep the chemicals in order. Faraday was super excited. यार कुछ तो है मिल रहा है. I'm getting to learn. I'll be in a lab. So he works in a laboratory assistant as for almost 2 to 3 years. And one day, right, people were magnetism that time was a craze. Right now, if you see last 2-3 years, say AI was the craze. So during that time, magnetism was the craze. People know about electrostatic fields and all, but magnetism was something new and people were going mad. So one day, some scientists were doing an experiment. There was a current wire. They kept a compass and they observed this compass ka needle, right, is deflecting perpendicular to the wire. Now we know, right, force will be perpendicular to the field. But during that time, when people didn't have an idea, these people were thinking if electrons are going like this, there should be an electric force in this direction. So the needle should be in this direction. So they couldn't understand and everything. They're getting confused. So Faraday, right, he tells them, sir, maybe the force is actually perpendicular to the field and all. He explains them. They look at him and say, like, you're a lab assistant. You better shut your mouth and be a lab assistant. Don't do extras, right? Typical, like them saying, nice story is pretty nice. We can make it into a good movie also. And Faraday gets really offended. He feels very bad. So that day night, he and one more assistant, lab assistant, they do an experiment. So this is something, I realized down the line, being a great scientist doesn't mean, you sit there and write theories. It is about designing an experiment to prove your hypothesis. Designing an experiment is the most difficult thing. Think about it, Rutherford. Everyone says Rutherford. The first thing when you hear Rutherford, you think about Rutherford Goldfoil experiment. You must have done many more, but that experiment, designing and getting an analysis out of it is the big deal. So this is the experiment. He took a magnet, north-south. He filled it with mercury. Why mercury is conducting? Then he took a battery. During that time, they used to use this chemical cells. He connected a rod here. So he connected the battery to this and another wire in the mercury. So when you switch on the battery, current flows through this, goes through the mercury, and the circuit is completed. And what he observed, Faraday, this rod started rotating in a circle. Now, if a rod goes in a circle, that means there must be a force toward the center, which is perpendicular, isn't it? Or else, why will a particle go in a circle? If a particle is going in a circle with a constant speed, that means the force must be perpendicular to the velocity. So he literally proved, boss, the force is actually perpendicular to the field. Getting it. And Faraday proved what he was saying, he proved it. But there's something more. Even Faraday himself didn't realize then. He did 3 great things. One, he invented the world's first electric motor. Isn't it an electric motor? This is the world's first electric motor. He didn't realize it. Getting it? Second, he proved a chemical energy can become electricity. Electricity can become mechanical energy. Mechanical energy becomes heat. He proved law of conservation of energy. Energy simply changes from one form to another form. Third, he proved the magnetic force is perpendicular. He proved 3 different things in one experiment. It was a mind, it was a mind-boggling thing. At that point of time, it was literally something else. Then he published this paper, right? He published this paper and that, and Humphrey Davy comes to know about it and pretty angry. He gets pissed off and say, "How dare you, lab assistant? How can you publish a paper?" and blah blah blah. Typical Bollywood story types. So in this movie, we can keep Humphrey Davy as a villain. We can try Sanjay Dutt or someone, and then And then Humphrey Davy, tells him to retract the paper, and Faraday doesn't agree. He says, "Boss, see, this is all the work that I did, right? And my friends are the ones who, helped me and everything. I can't back down now." So Humphrey Davy starts, slandering him like, this guy copied everything from a German scientist and everything. So Humphrey Davy starts spreading rumors. So Faraday actually goes to the German scientist and he talks to him and asks him, "Is this what you did?" And that guy says, "I have no idea what is this." So he gets a statement from the German scientist that it was all Faraday's original work. And then the paper gets published. And after 3-4 years, right, Faraday work was so, what do you call it? It was groundbreaking at that point of time. He goes really ahead. And after 4 or 5 years, he actually becomes the head of the Royal Society of London, displacing, Humphrey Davy. So he becomes the head. Then after that, whenever people talk about Humphrey Davy, when they mention Faraday name, Humphrey Davy used to get pissed off and say, like, I'm greater than Faraday because I am the one who found Faraday, so I'm greater. That was his famous statement. And then, finally, Humphrey Davy passes away, and Faraday continues working for more than a decade or so. He does a lot of things, and one day, right, he makes a statement in the thing, like, light is an electromagnetic wave. And people are like, what the hell you're talking about? Like, what is the proof? Now, this guy Faraday, right, was intuitively a genius. Matlab, he knows, he feels it. Sometimes hota hai na, but you can't explain. He was that type of a person because he was not formally educated. Whatever he learned is by experience and instincts. This guy figures out light is an electromagnetic wave. He didn't have a proof. It takes him 13 years. After 13 years, he meets a young man called Young's Maxwell. Heard about his name? Maxwell. Maxwell, equations and everything we will see later on. Maxwell is a brilliant mathematician. So that is one thing. If you're planning to do research in physics, you should be a very good mathematician. At some point, right, when you go to MSc and all, it becomes more of a max. You need to be very good at math. So this Maxwell, right, is working on a topic called groups in Max. So to simplify, what he was studying was if a property A creates property B and property B creates property A, and this happens continuously. This always happens at a particular speed. So that was the summary of that entire theory that he was studying. When he applied this theory to electric and magnetic fields induce magnetic fields induce electric fields. This happens at the speed of light. Now you tell me, if light was not an electromagnetic wave, why the hell electric field and magnetic field are oscillating with the speed of light? And from there, he proves all that thing in one page, and he gets something in a formula 1 by root mu naught epsilon is equal to C, which I showed you in the last class. Just look at this formula. Mu naught is magnetic permeability, epsilon is electric permittivity, C is the speed of light. That one equation tells you that speed of light depends on electric and magnetic fields. And that was the proof that light was an electromagnetic wave. And Faraday had to wait for 13 years for someone to come and prove that. So Faraday's story was quite interesting. If you get time, you should definitely watch the documentary. You can do that once your advanced exam gets over. You'll have 2 months time. Anyway, so that was the story about Faraday. Yeah, whenever I see that thing, right, I really feel like, yeah, what kind of person is that guy? From a book binder, he becomes the head of a Royal Society of London. So goes on. So Faraday, right? So when he was working on EMI, electromagnetic induction, this was the experiment he was kind of doing. So we have an ammeter here. So we have a coil and we have a magnet. So if you keep the magnet at rest and if you keep the coil, nothing happens. So there are magnetic field lines. You will observe nothing happens here. There is no current. Fair enough. But now the same thing. North, south, north, south. This time, if you move the coil, if you bring the magnet towards the coil with some speed V, you observe there is suddenly a current and the needle starts deflecting. If you move the magnet away from the coil, you'll observe the current goes in the opposite direction. There is again a current. So whenever the magnet moves, the magnetic field changes and there's a current. Now, again, Faraday has no idea why this is happening. Like I said, completely experimental. He derived everything from experiments and he has no clue why this is happening. You ask him, boss, why is this happening? He says, I have no idea. So this guy is something like Archimedes. Archimedes knows there's something called buoyant force, but he has no idea why it is coming. At that point of time, people didn't have maybe enough knowledge. So Faraday knew whenever you mess up this magnetic field, there is a current being generated, but he doesn't have an idea why it is coming. We will see this later on. This is one case. Second case, he also observed not only in this scenario, let's say you take this coil, you keep the magnet at rest, but this time you change the area. Let's say you increase the area of the coil, you make the coil bigger or smaller. Even then we notice there's a current flowing. Third, you also noticed, again, magnets are not moving here. Magnet is at rest. But this time you rotate the coil by some angle and you observe again there's a deflection. So one thing is clear. Whenever the area changes, there is a current when the area changes or the angle changes. So that means we have no idea why this is happening, but whatever current is being generated is depending on the magnetic field, it is depending on area, it is depending on angle, it is depending on B, A, and theta. What quantity is this? Flux, isn't it? So the story goes actually the other way around. So from here we call this flux. Are you getting it? But I started the topic with the flux and then I came here. But technically it is the other way around. I know it depends on B, I know it depends on area, I know it depends on theta. When I combine these three, I call it flux. Then I say, boss, this is depending on flux, magnetic flux. So there's a current when area or angle changes. So when he combined all these things, he ended up with a result. So he came up with a few conclusions. First thing he said, okay, there is a current. Now understand, in the experiment, you always see the current. But we know if you want to get a current, there should be an EMF. That means somehow this is generating an EMF, electric EMF. Again, how? We don't know. But it is happening. EMF is induced, and he proved this EMF induced is given by minus d phi by dt, where your phi is nothing but flux, which is n into integral b dot dA. N is the number of turns, b dot d is the flux in one loop. And here the negative sign indicates opposition. We will talk about that. So that's your final statement. So what is Faraday's law of electromagnetic induction? EMF induced in the loop is proportional to rate of change of flux. So this guy figured all this stuff with experiments. This is our second formula, everyone. The flux is integral n dot b dot dA. EMF induces minus d phi by dt. So this will give you the magnitude. Let's see how to get the direction though. Any doubt so far? Then come Lenz's law. Basically, that's your minus sign. Idea is pretty simple. It's kind of like Newton's first law. Whenever there's a change, there is always an opposition. You need to apply a force in order to make the system change. Similarly, if the current or the EMF induced, any system, right, doesn't like change. Whenever you want to change, there'll be always a kind of an opposition. So the current or the EMF that is induced in a loop in such a way it opposes the change in flux. Again, understand, I don't have a problem with flux. We have a problem with the change in flux. So what it means, to put in simple words, if flux is increasing, system will try to decrease the flux. Again, system will try, whether it can decrease or not is a different story. If flux is decreasing, system tries to increase the flux. Clear? So let me show you with an example. Listen to this thing. So let's say we have a loop here. Let the radius be A. Let the magnetic field be B is equal to B naught T. So first thing, find the flux. So flux will be B naught T pi A square. Get the magnitude. I'll just get the, so always just get the magnitude with this formula. Direction we'll figure out. This will be B naught pi A square. So this is the EMF induced in this thing. Now there are two possibilities. One, the battery could be in this direction. Two, the battery could be in this direction. So basically current is flowing clockwise or current is flowing anti-clockwise. These are the two possibilities, isn't it? Either you go clockwise or anti-clockwise. Now let's see what happens in both the cases. Now we know B external is into the plane. Now using right hand thumb rule, this B induced, the green current is producing field in which direction? This green one is also producing field in the downward direction, isn't it? So whatever current that you produce will be also downward. Now because of this, what will happen? The net field will actually increase. B external plus B induced. So the overall field is increasing. So here, flux increases more. Because the flux increases more, then this will create actually current increases more. So B induced increases, so flux increases more. Therefore, I increases. If I increases, B induced increases. If B induced increases, B net increases. This will again increase the flux. This will again increase the current. This kind of systems are called positive feedback loops. These things don't exist in nature. Problem with this, if the current just keeps on increasing, eventually I will tend to infinity. The system is producing free energy, isn't it? Means once you start the system and leave it, this will just keep on increasing forever on its own. right? Energy becomes infinity. You have disobeyed law of conservation of energy. This is not possible. In this case, this is not possible. You will have an issue here. But look at this guy here. B induced is outside. So I'm not saying you can't support every time. In this case, you can't, because that guy is also increasing. You're also increasing. You'll mess up the whole thing. The B external is downward. If you can see, both are opposite. So B net will be B external minus B induced. So if B external tries to increase, B induced will increase. It will decrease the overall, this thing. So here, flux is increasing. So here, the B induced will decrease. So here, B induced opposes the increasing flux. This works for us. This is the kind of thing we need. This is a negative feedback loop systems. These are very important. Later on, you'll study. If you're in electrical engineering, right, you have a subject called control systems. We actually use this every day. We don't realize it. Imagine you're designing a robot and you ask the robot, give me an apple. So it takes an apple and just pushes that apple into your head. It just smashes your head like this. Now, the problem with that thing is you wrote the program, give the apple, right? You need to put a negative feedback loop there in the programming and tell them, as the hand gets closer and closer to the target, your speed should slow down. You're getting it? It is not as simple as saying, take the hand and put it there. If you do that, when the hand reaches there, the robot will think I have followed the instruction, but you forgot, boss, there is a velocity now, and that's not going to stop. It will just smash into your head. You do that. When I ask you, give me your pen, how do you give? You take it gently and put it right, or will you take the pen and poke me directly? So when you're designing systems, you need to take care of all that. So designing a robot is not a joke. That is a problem. People just think I'll put some motor and everything. You need to have a lot of damping. Remember, I taught you that in damping oscillations. I told you there is an over damping. There is a factor. So you need to design the robotic arms with over damping. Once it stops there, it should stop there. Nato, your hand will just keep going like this up and down. You'll start oscillating like SHM. So all that stuff. Clear with this? So you guys try this. I'll give you one more example. Let's say we have an infinite wire I. Let's say we have 3 loops. This loop is going like this. This loop is coming towards. This loop is going up. Can you tell me the direction of current? Clockwise, anti-clockwise. That's it. Just the direction. What is the direction of the current in the 3 loops? Again, remember, my job is what? If the flux is increasing, I'll try to decrease you. If the flux is decreasing, I'll try to increase you. That's my job. My job is not to oppose you. Kind of like friction, right? Friction does not oppose motion. It opposes relative motion. If there are 2 bodies going, the one who goes faster, I'll try to decrease that guy. One who is going slower, I'll try to help that guy. I'll do something similar. Down क्या है? Clockwise, anti-clockwise बोलना है. Down up क्या होता है? See, first of all, get the direction of the field. The field is downward. This is your B external. I'll write down the steps in the next page, but for now, let's see. So this is your B external. Great. Now this guy is going away. So if you go away, remember the magnetic field is mu naught I by 2 pi x. Means the farther you go, lesser the magnetic field. So in the first case, flux decreases. Therefore, B induced will support B external. That means B induced must be in the same direction as B external. So B induced also will be down. If B induced is down, then use your right hand thumb rule. Take your right hand, put the thumb in the direction of magnetic field, rotate your fingers. Then you get the current in anti-clockwise, ACW. Is that clear? In the second case, loop is getting closer to the wire, so B increases. If you get closer to the wire, B increases. If B increases, flux increases. If flux increases, I want to decrease it. Therefore, B induced opposes B external. That means my field should be out of the plane. Put your thumb out of the plane, rotate your fingers. You will get clockwise. Third case, flux is constant. If you're going straight up, magnetic field at a point does not change. Therefore, current is zero. Clear with this? I wrote wrong, na? Sorry. This is clockwise. This is anti-clockwise. I wrote reverse, my mistake. Clear with this? I was saying clockwise, but I wrote direction wrong. Clear with this? Take a break. Come back by 9:40. We'll continue from here. Any doubts so far? Chalo, come back in 5 minutes. How do we find EMF? Step one, calculate the flux. Right. And then find the magnitude, d5 by dt. This will give you the magnitude. Step two, check whether the flux is increasing or decreasing. Step three, check the direction of B external. If flux is increasing, B induced is opposite to B external. B induced is in the direction of B external. Then use your right hand thumb rule. Where you are, your thumb is the magnetic field and the curl of the fingers is the current direction. Thumb indicates B induced. Curl of the fingers indicate current or the EMF. Clear? There, you follow the steps, you will get everything. This is the biggest headache in the chapter, like the starting part. How do you get the direction? Clear with this? So let's see a question on this, and I'll show you something. So let's say we have a fixed coil here. We have a magnet north south coming this way with V. Observer is here. So if you ask this observer what is the direction of current in the loop, what will you say? This is important. Where is the observer? Because if the observer stands here, clockwise, anti-clockwise will get reversed. So the loop is on your table, magnet is coming from the top. So you're looking from the top. You're the observer. What is the current in the loop, clockwise or anti-clockwise? I don't care about the magnitude, only the direction. Let's see. Step one, what to do? We don't want the magnitude anyway, so let's get the direction of the field lines. So how will the field lines look like for a magnet? The lines go like this. Now you tell me, if you're getting closer, is the flux increasing or decreasing? Flux increases. This is your direction of B external. So the flux increases, the coil doesn't like this. So the coil will generate a field in the opposite direction. Both should oppose. So B induced opposes B external. Now that means what? It is going up, isn't it? Put your thumb towards you. Put the thumb towards you and rotate your fingers. What is this direction? Anti-clockwise, isn't it? Therefore, current is anti-clockwise. Is that clear? The observer will think B induced is towards him. The thumb is pointing towards his face. So if you put your thumb towards your face, the fingers will go anti-clockwise. And there's something more interesting here. Look at this. So this magnet is coming down north-south. If you look at this coil also behaves like a magnet, north-south, so both will repel. They both repel actually. So if you take a magnet and leave it on top of a ring, it gets repelled. That means if you actually try to look at the forces, this will have mg, this will have a magnetic force. Therefore, this acceleration will be less than g. So if you take a magnet and leave it, this would be a proper mains level equation. What will be the direction of the current and what will happen to the acceleration? Equal to g, greater than g, less than g. It will be less than g. So the magnet actually slows down. Clear with this? All clear with this page? Same thing, you guys do this. What if the coil is there? This time the magnet is crossed and leaving it. Observer is still here. Find the direction of the current. And what about the acceleration? Will it be less than g, greater than g, or equal to g?
So velocity का direction.
It's going away, right? It's coming down. It has crossed it. So how will the field lines be here? The field lines will come towards the south pole. That means your B external, the flux is decreasing. Therefore, B induced supports B external. So B induced also must be in this direction. B external is in this direction. So if you actually look at this would be south and north. This would be north and south. So this time they attract. That means the force is still up. Mg is down. So acceleration will be less than g. It still slows down. And what about the current? Put your thumb down. So this guy will see clockwise. Is that making sense? I can give you another reason why A will be always less than G. Listen to the logic. It comes from energy. When the coil is falling, you're generating a current in the loop. Agreed? So if you're generating a current in the loop, means you're increasing energy in the loop. And now you're saying acceleration is greater than G. That means your energy is also increasing. Where the hell are you getting all this extra energy from? So someone must be losing energy to create energy in the loop, na? That means the magnet cannot fall faster than G. So whatever energy the magnet is losing, it was supposed to fall with G, but it is falling less than G. So where is that extra energy going? That extra energy was going into the loop. You're getting it? So remember this thing. Sometimes when you see a question and you're not getting what the hell is happening, energy is always there. You cannot create excess energy out of nothing. So that is how you should think. When what about acceleration? You can never have greater than G case. If you have A greater than G, that means this thing is going faster than it is supposed to go, and you're, on top of it, you're generating current in the loop. You are getting excess energy out of nowhere. Clear with this? That was the reason the flux was always opposing it. So the flux is actually the B induced is stealing energy from the system and it is giving it to the loop, something of that sort. But remember this logic, quite useful. Same question. What if I ask you like this? Let's say this time magnet is like this, north, south, and going this way. Now what? Magnet is little to the side. You can see this is exactly midpoint, and then now what? No, Puroja, you need to see change in flux, isn't it? And all the lines are entering or not leaving. Don't do like that. You are entering. That's it. You're not leaving. No, leaving matlab again you have to cross. You're crossing the surface. You're again crossing the surface. See, when you have like this, you crossed it. You entered. You left. ऐसा count करना है. You can't count as entering and leaving. Got it? You have to cross into and cross out. Here, look at this problem. In this, the most common mistake, right, is the direction. People mess up the direction. How are the field lines here? So if this guy is going down with V, this is like this. The field lines are going like this, na? B external is actually upward. That is the mistake. That's it. Then it is done. So if it is going away, flux decreases. So B induced will support. That means B induced also will be up only. So this is looking at me. So this is anti-clockwise. Clear?
Sir, how did you get that the flux is decreased?
Because it is going down. Now, if it goes here, then what will happen? Less and less lines will enter, isn't it?
Okay.
There will be more density na, here. Here I'm not drawing it, but there are more lines like this.
Yes, sir. Thank you, sir.
What about this guy? This time instead of a ring, let's say take a long copper rod. Long hollow copper pipe. Gravity is there. You took a magnet and you dropped inside. Plot velocity time graph. Something happens. Approximately plot VT graph. The reason to take copper is because you don't want the magnet to, get stuck to the metallic rod. If you take a steel pipe or something, iron pipe, the magnet will go and get stuck. So we don't want such things. So copper is still conducting, but it is non-magnetic. Approximately plot velocity time graph. And these are good theoretical questions. Nah, re Aditya. You're forgetting there is an MG also sitting there. MG क्या करेगा? Dance करेगा. Nee, re. Why will velocity be constant? That will happen, but not immediately. Let's see. So this magnet, when it is falling, just now we saw in the first two problems, all the coils in front of you will repel, isn't it? The coils in front of you will repel. The coils behind you will attract. That means if you look at the forces acting on this, you have the magnetic force. So this is called as magnetic drag, just like viscous drag, mg, and this is acceleration. And you will observe the faster it goes, initially there is no velocity, so there is no magnetic drag. But because of mg, speed increases. As speed increases, rate of change of flux increases. That means they'll induce more and more currents. Right? Flux changes faster. That means your magnetic drag increases. And eventually, the magnetic force becomes equal to mg. It kind of behaves like viscosity. After a long time, in real life, you'll have air resistance and all that, but technically, eventually, F magnetic will become mg. At this point, your velocity becomes constant. So if you try to plot this graph, this will look exactly like viscosity graph of a ball dropped in a liquid. You'll get a VT graph. So it increases, and becomes constant. You will reach a terminal velocity. Yeah, we can't find this, but yeah, graph looks like this. You'll reach a V terminal. If they ask you to plot acceleration time graph, you will start with G and then decrease, and go off. This is your acceleration time graph. Do you remember same graph you drew in viscosity? It reaches terminal velocity eventually, not initially. Clear with this? All got this?
In 1831, Michael Faraday in London and Joseph Henry in New York loop, 10 loops.
There, this is a Faraday skull thing. So he has taken 1 loop, 10 loops, and 100 loops. So,
and
we have an ammeter, and he got a magnet.
I now have the single loop coil connected to the ammeter, and I'm going to move the bar magnet into and out of the coil. And if you watch very closely, you can see a slight deflection.
It's a very small deflection.
The ammeter needle.
It's moving. I'll post the video in the group. You can check it out.
It's
a very small deflection. So let's put a little bigger one. 10 coils, you'll get 10 times more EMF, so you'll get more deflection.
I'm going to do the same thing. I'm going to move the bar magnet in and out of the coil. Now you can see more.
Can you see the deflection?
Of the needle. In fact, if I go
Are they able to hear,
slowly, you see just a little bit of a deflection, And if I go quickly, you see a greater amount of deflection.
Can you see it is going in the opposite
Also,
direction?
as the magnet is going in, the needle deflects to the right, and as I pull the magnet out, it deflects to the
Let's see with the
left.
100 one,
When
that
the
is more
magnet,
clear.
okay, so 100 loop coil. And I'll start by moving the magnet in very slowly. You see
See,
it deflects
even when
to
you
the
move slowly,
right,
it deflects a lot.
pull it out to the left. And if I go in quickly, you see a much greater deflection. Okay, so the rate of change of the magnetic field affects the current also.
Clear that? So there, it is not our imagination, it does actually happen. Right? So this is another good one. This is the problem we did right now. So you took a copper cylinder, it's a pretty thick one, so it's like a lot of coils, so you'll get terminal velocity very fast. Measuring the length around 10 centimeters, around like 2.5 centimeters dia. This is a neodymium magnet, so these magnets are pretty strong, right? You use them from very far, they will actually break themselves. There, see, it is not attractive. So copper does not attract any magnets. So we are making sure. Let's see how it goes. It feels like it is just floating. It looks like nice. When he drops it, you can see literally it takes time. This you can see more clearly. See. Look at this. This you can see more clearly. Look at that ring. Huh? It literally floats. There is some lag, I guess. But I'll post this. You can check it out. So this is a question we did. The magnet literally floats and goes aram se. So it does actually happen. So in some European amusement park, right, they have a ride, which is something like it goes straight. I think it just goes straight and then it spirals actually, something of this sort. Right. And the problem with this thing is when it comes back with a speed of around 160 kilometers per hour. Now at that speed, if you try to apply brakes, right, there is a high chance of a mechanical brake failure. The brake might get ripped off, or or you have to keep replacing the brakes a lot. So what these people did, when it's coming down, they switch on the magnetic fields. You have a magnetic region. So once it enters here, this magnetic drag will actually slow you down, and there are no moving parts, isn't it? That's the best part. So in this braking system, there are no moving parts. So there is no chance of a mechanical failure. The only thing is the whole ride becomes a little hot. That energy has to go somewhere. It actually becomes heat. Getting it? And then once it reaches a speed of around 80, 90 kilometers per hour, then they apply the brakes. So they actually use the magnetic drag while coming down to slow it down. And then they apply the regular brakes once it reaches a decent speed. So it has actually a lot of practical applications, magnetic braking. The same way, like, when you're taking a lift up and down also, I think there is a chance, like, maybe you can make a lift without any wires in the future. This is one. Let's see one more theoretical question. Let's say we have a loop with a switch. And you have one more coil here. So we have coil 2. We have coil 1. This is a switch. Now, the moment you close the switch, the question is what happens when you close the switch? Options will be, will they attract, will they repel? Nothing happens. It depends on the direction of the current. So options will be of that sort. Remember coil 2, there is nothing, no battery, nothing is there, it's just a conducting coil. What do you think will happen? Let's see. Deflection क्या होता है रे Vignesh? See what happens. The coils, something happens between the coils. So the moment you switch it on, the current will flow through the coil. Then we get a magnetic field. Now this is okay. Now, if you ask coil 2, boss, what happened? What will coil 2 say? Coil 2 will say initially had no flux. Now out of nowhere, suddenly there is a flux, isn't it? And the coil 2 is not happy about it. So coil 2 will generate a B induced opposing it. Flux increases suddenly. That means this will act like a magnet north-south. This will act like a magnet north-south. They will repel. The second coil will just fly off. What if the current is in the opposite direction? Story is still the same. If the current flows this way, this will be your B external. So still, end of the day, flux though increased. This guy is not happy about it. So this guy will do a B induced in the opposite direction. So this will be south-north. This will be north-south. They will still repel. Clear with this? In both the cases, it will repel. Doesn't matter which way the current flows. Any doubts on this? So can you see what we're doing? We are combining EMI with the, creating magnetic field of a coil and all that stuff. So there, they can ask theoretical questions like this. So this entire fourth question is all theoretical stuff. You get some pretty good questions like this. Let's see one more. Let's say we have a circular coil. It goes over this. This is resistance R, this is resistance 2R. They are circular coils. I couldn't draw them well. This is 2A and this is A. In the middle, it is jumping over it. They're not crossing each other. The magnetic field is B naught T. Here also magnetic field is B naught T. Find the current in the circuit. So you have twisted the coil in the middle. So you can basically treat this as one coil and treat this as one coil and find the EMF for them separately and then try to join it back. Think, I'll give you a minute. नहीं रे, zero क्यों होगा? Both the coils are not same size. Area same ले लिया तूने. So you can treat each coil separately. So what is the first coil ka flux? First coil ka flux will be B naught T 4 pi A square. So EMF will be B naught 4 pi A square. What about the direction? Flux is increasing. So you want to oppose this. So B induced will be out of the plane. That means current will flow anticlockwise. Similarly, here also flux 2 will be P naught T pi A square. Here the EMF E2 will be B naught pi A square. Here also the current will be clockwise, anti-clockwise. So both of them are trying to push anti-clockwise. So this will be like a battery here, E1. This will act like a battery here, E2. Now look at the problem here. When they try to push the currents, this guy is trying to push the current I, it is going opposite to the battery. Basically, both the batteries are fighting. So which battery will win? The one with the bigger EMF will win. So we get the current I will be E1 minus E2. Resistance will always add up 3R. Clear with this? This current here is opposing this battery. If you apply Kirchhoff's law in this, E1 is forward and E2 is opposite. So it is E1 minus E2 is the net EMF and the total resistance. Once you get EMF, your current electricity will come. Is that clear, everyone? If I want them in the same direction, then the picture would have looked like this. Like this, no? If I have drawn like this, they would have added in the same direction. This would be E1 and this would be E2. Here I would have been E1 plus E2 by 3R. Clear? Next one. We have a rhombus here. Of side L. A, B, C, and D. Then someone started pulling this with speed U. You know what will happen, right? If you pull like this. After some time, the shape becomes like this. And eventually, this is how it would start looking. So here, what is getting messed up? The area. And let's say magnetic field B is constant. And let this angle be theta. So point C is pulled with constant speed U. Find the EMF as function of theta. The only thing that is there, flux is d phi by dt. Everything else is mechanics. Story is still the same. What is flux B dot area? Then differentiate. Get this, you got 2 minutes. The moment you do d phi by dt, EMI is over. Try. Get some water and come. Give it a try. Step 1, find the flux as function of theta. So this will be in the middle. So if you talk a perpendicular here, this is L, this is L cos theta, this is L sin theta. So there are four triangles there. So flux will be B into area will be half L square sin theta cos theta into 4 times. Therefore, that will be BL square sin 2 theta. Perfect. So EMF, I will just take the magnitude for now, BL square cos 2 theta 2 times d theta by dt. We are stuck with d theta by dt. How do we get d theta by dt? If you look at this distance here, this is your horizontal distance x, which is 2L cos theta. So if you differentiate this dx by dt, that will give you velocity of point C. That will be minus 2L sin theta d theta by dt. From here you get d theta by dt, which is actually your angular velocity, isn't it? So from here we get d theta by dt is equal to minus u by 2L sin theta. Take that and substitute here. And I will just put a minus sin d phi by dt. Here the signs will take care of themselves. Minus minus goes off. BL square cos 2 theta 2 into u by 2L sin theta. This will be BLU, 2 also goes off. You end up with cos 2 theta by sin theta. You can write cos 2 theta as 1 minus 2 sin square theta. That will be 1 by sin theta minus 2 sin theta. You can do maximum minima. You will notice at theta 45 degrees, you get maximum EMF. That also they can ask you. Find the EMF as function of theta and find the maximum EMF. So this thing, when it is going towards theta, the EMF will go to maximum and then again it will start decreasing. So if I try to plot a graph, yeah, that's a cos 2 theta by sin theta graph. So I don't know how the graph looks, but I'm sure it will increase and then decrease. Aisa kuch hoga. And that I will happen at 45 degrees. Clear with this? Clear with this? So the main thing was this, finding the d theta by dt. Next thing. So here you're messing up the area. So till now you're messing up the magnetic field B with time. This you're messing up the area part. Then your favorite spiral. Third time. Comes 3 times, but it comes back to back actually. Inner radius is A, outer radius is B. Resistances are. Find the current. Magnetic field is B naught T. No, it's a function of theta, na? Time will be a mess, I guess. You can still find, I guess, that x is 12 cos theta, na? 12 cos theta, and this will be equal to ut. So you will get something from there, but it is messed up. Get this spiral, I already taught you 2 times. Let's see. You have to find the flux. Here, there are 2 different things here. Remember, when you use Faraday's law, you have to differentiate with respect to time. So how do we do these things? So at a distance x, we take a thin loop. Distance x dx. So the flux will be number of turns per unit width into dx. This will give the number of turns. The magnetic field is B naught T. The area is pi x square. Be careful, A must be area of the loop. Don't take 2 pi x dx. Isn't it? When you say flux, this is the area where the field is passing through. You should take that area, the area of the loop. So now when you integrate the flux, you are integrating with respect to x. So during that time is constant. So you integrate flux with position, the x coordinate, and then differentiate with time. So this will be n by b minus a b naught t pi integral x square dx from a to b. This is n b naught pi b cube minus a cube by 3 times b minus a time. Therefore, EMF will be differentiate this. I can get the magnitude, I can get the direction from Lenz's law. Clear with this. Since the flux is increasing, my current will try to oppose it, therefore you'll get the direction. It should be anti-clockwise. Clear? Yeah, that's how you handle it. The 3rd time, I don't think you'll see it again, but yeah. You see a spiral, that's the idea there. Next thing, an AC generator. So let's say we got a coil here. The coil is rotating with omega. So let this be area vector. Let's say in this case, I'll keep B constant. N turns. Radius is A. Resistances are. In reality, if you go to a power plant, what you see, right? They keep the coil fixed. They actually rotate the magnets. They keep the coil fixed and the magnets are rotated. So B bar turns, whereas A remains constant. So currently the power you are getting is actually coming from some power plant where a coil is rotating. So this coil is rotated. In a hydroelectric power plant, we use water to rotate the coil. In a thermal power plant, we burn coal, we get steam, and that steam is used to rotate the coil. In a nuclear power plant, we use the nuclear reactions to produce heat, and then that produces steam, and that rotates the turbines. So a nuclear power plant is nothing but a glorified thermal power plant. Instead of using coal to burn, we use nuclear fuel to produce that heat. So technically, if you see, the only way we humans can produce power at a massive scale is rotating the coil. So find the EMF of the coil. That's an easy one. Find the charge that flows through the coil in half revolution. This is a very good mains level question. Comes a lot. So how much charge flows through the coil in half revolution? Let's get them both. Yeah, this is straightforward. Look at the first one. So here flux will be number of turns N B A cos theta. EMF will be minus NBA, that will become minus sine theta d theta by dt. So whenever you get something as a function of theta and all, let the minus sign be there. That will take care of itself. So d theta by dt is nothing but omega. So NBA omega sine theta is nothing but omega t. There, this is how you generate your AC current. That NBA omega will be 220 root 2. That is, we will see in AC. That's your 220 volts. And that omega will be 2 pi f. F is 50 hertz. How do you get charge there? Now we know E is d phi by dt. So if you divide by resistance on both the sides and multiply dt, this will become 1 by r d phi. This will become I dt. So if you put an integral on both the sides, we get I dt will be integral d phi. I dt is nothing but charge. This is delta phi by r. There, pretty important formula. So charge flown is change in flux by resistance. Definitely remember this. Asked multiple times, multiple exams. So in our question, you're rotating by 180 degrees. So change in flux will be BA, NBA minus of minus NBA. Angle becomes 180 degrees by R. 2 number of turns BA by R. We are multiplying N everywhere because the number of turns. Clear with this? Half revolution, so theta is 180. Yeah. Same thing. I can ask you another model in this. Suppose, let's say the right side is having a constant magnetic field. We have a coil here, semicircular coil. This is hinged in the center. And this is rotating in this direction with omega. Meaning after some time, the coil becomes like this. And then after some time, it becomes like this. Then after some time, it becomes like this. Then it becomes like this. Then it starts coming out. You're getting this coil is, next moment it starts coming out. Plot EMF versus time graph. So, and assume take anti-clockwise as positive. If I mention something like this, then it is fine. Then you have to take your directions. If I don't mention, then just leave it as theta. So here we have a coil rotating with omega in the plane. Questions clear? Finish off, last one for the day. So when it is entering, this will be theta. So we are interested in this area here. What is the flux? Magnetic field B is constant. And what is area? Theta r square by 2. Remember area of a sector? In case you don't know, then 2 pi will give you pi r square. Then theta will give you how much? You can use unitary method. So you're done. So EMF will be B r square by 2 d theta by dt. It's constant actually. So B r square by 2 omega. Constant, great. And this is where people goof up after this. The direction gets messed up. So when you're entering, the flux is increasing. Therefore, B induced will oppose B external. B external is inside, so this is out. So this is anti-clockwise. This is great. This is when entering. But what about when you're leaving? When you're leaving, if you see this coil will become like this. So this is the scenario when it is entering. This is the scenario when you're leaving. So still the same story. Now, if you see the flux decreases. So B induced will be crossing. So basically every 180 degrees, the current direction will keep changing. So if you plot the graph of EMF versus time, so initially it was clockwise, anti-clockwise, positive, then negative, then positive, then negative. You get constant, but the sign keeps changing. So this happens for pi by omega, this happens at 2 pi by omega, and so on. Every pi by omega, it changes sign. Clear with this? So that is the mistake generally people do. When they see this constant, they think, oh, constant, so they'll just draw a straight line. The direction changes, so be careful with that. This is another way of getting an alternating current whose magnitude is constant, but the direction keeps changing. Clear with this? There. So that is how we can do. This is also kind of an AC generator. The next class when we catch up, we will do a few more on this, and then we will go for the next part, something called motional EMF. We will see the reason why you're getting this EMF and all. Next class will be important. We have much higher level problems there. But please make sure to go through the notes. A lot of theoretical things we have done today, right? So check it out and see if there is anything that you're not clear, ask me in the next class. Okay, with that, we'll wrap up for the day. We'll catch up again on Friday. We'll continue from here. And do remember, there's a test online on ray optics, so do make sure to give it. So any doubts?